in the lab. If there is any difficulty recovering a full sample, the split spoon may be fitted with a wire or plastic core catcher. In order to better preserve the samples, liners made of either brass, stainless steel, or plastic may be inserted into some split spoon samplers. A relatively simple and standardized method for estimating the compactness or stiffness of the soil in situ is the Standard Penetration Test, or SPT. This test consists of counting the number of blows of the hammer required to drive the split spoon sampler a specified distance into the ground. The essential features of the SPT test include a drop hammer weighing 140 pounds, falling through a height of 30 inches onto an anvil at the top of the drill rods, and a split spoon having an external diameter of 2 inches and an internal diameter of 1 3/8 inches, and a length between 18 and 30 inches. After the spoon is positioned on the bottom of the hole, the number of blows of the hammer required for 3 successive 6-inch penetrations are counted. The number of blows for the second and third 6-inch increments are added together to obtain the standard penetration resistance, or N value. The number of blows for the first 6 inches is not included in the N value since it may be affected by disturbed soil at the bottom of the hole. It is still recorded, however, as it provides a useful check on the variability of the deposit and the consistency of the overall results. There are numerous factors that can greatly influence the N value, and thus the field engineer must pay careful attention to the manner in which the SPT test is performed. Some of these factors will now be briefly discussed. Mud rotary drilling is preferred over hollow stem augering. If hollow stem augering is used, the hollow stem must be continually filled with water or drilling fluid to an elevation above the surrounding water table. Otherwise, inward seepage of water at the bottom of the hole could loosen the soil, thereby causing N values to be unrepresentatively low. This inward seepage could also erode soil into the auger stem, which, if mistaken for the bottom of the hole, could cause N values to be unrepresentatively high. It is recommended that the diameter of the borehole be 4 to 5 inches. As the diameter of a borehole is decreased, the penetration resistance is likely to increase. Side discharge bits should be used when rotary drilling because the jetting action of a face discharge bit disturbs the soil at the bottom of the borehole. Most drill bits can be modified to be side discharging by spot welding on baffles to deflect the drilling mud sideways. When sampling at depths less than 50 feet, A or AW drill rods with an outside diameter of 1 5/8 inches should be used. And for depths greater than 50 feet, N or NW drill rods with an outside diameter of 2 5/8 inches should be used. The heavier N or NW drill rods are recommended for the greater depths to maximize the transfer of energy from the hammer to the sampler. The split spoon sampler must have an outer diameter of 2 inches and a constant inside diameter of 1 3/8 inches. Liners may be used only in modified split spoons that maintain a constant 1 3/8 inch diameter inside the liners. If a modified split spoon with room for liners is used without them, the N values are generally 10 to 20% smaller. The amount of energy delivered to the sampler per hammer blow should be 2,520 inch-pounds, which is 60% of the theoretical maximum. The amount of energy delivered is dependent on many variables, including the type and weight of hammer, distance of free fall of the hammer, size and length of drill rods, tightness of connections, weather, and operator. If using a cat head and rope, the energy also depends on the condition and type of rope and the number of wraps around the cat head. If using a trip hammer, the energy also depends on its condition and type. The amount of energy delivered can range from 30% to 95% of the theoretical maximum. Since the N values are inversely proportional to the energy delivered, energy ratios of 30% to 95% can cause N values to vary by a factor of 3 or more. Mechanical trip hammers provide a more repeatable energy input, while the energy from drop hammers can vary as the driller becomes physically tired and slowly reduces the hammer drop height, number of blows per minute, and other variables. Thus, it is highly recommended that the energy delivered by a particular drill rig be calibrated on important projects. The blow count rate, or number of times the hammer is dropped per minute, can also affect the N value. During sampler penetration, negative or positive pore pressures may develop in the soil. A low rate of blows will permit more of the excess pore water pressure to dissipate between each blow than can occur with a faster blow rate. The result is different effective stresses and thus different end values. A rate of 30 to 40 blows per minute has been recommended. Even if these additional recommendations are incorporated in the already standardized standard penetration test, the results still only provide an indirect measure or indicator of the compactness or stiffness of the soil. Therefore, an engineer must be cautious in performing the test and analyzing the results. Thin-walled Shelby tubes are commonly used to obtain high-quality or relatively undisturbed samples. An undisturbed sample is one obtained with sampling techniques designed to preserve as closely as possible the natural structure of the material. These samples are suitable for shear, consolidation, and permeability tests, as well as for all tests performed on disturbed samples. However, a certain amount of sample disturbance is inevitable, regardless of the sampling method used, and thus the term undisturbed sample is only a relative term. Thin-walled Shelby tubes come in diameters from 2 inches to 3 inches. Commonly have a length of 30 inches and may be made of galvanized steel, stainless steel, or epoxy-coated steel. Tubes of much larger diameter can have difficulty retaining the sample. The lower driving end of a thin-walled tube is beveled to a cutting edge, creating a slight inside clearance. The upper end is attached to the drill rods using 4 hex screws and an adapter. To take a sample, a tube is attached to the bottom of the drill rods and lowered into the borehole. The sampler is then pushed downward from the bottom of the hole a distance about 5 inches less than the length of the tube. To minimize the sample disturbance, the sampler is pushed into the ground at a high constant speed. The sampler should not be driven by a hammer, as this increases sample disturbance. After the sampler has been pushed down, the drill rods are rotated to shear the end of the sample, and the sampler is removed. Excess soil at each end of the sample tube is carefully cleaned away, and metal discs are inserted to protect the faces of the soil sample. Microfine wax is then commonly poured against the metal discs to form a seal. Alternatively, special O-ring packers may be inserted against the soil inside the ends of the tubes, and then expanded to form a seal. Tubes are then stored vertically in a padded box for transport to the lab. Some disturbance to tube samples is caused by the in situ soil being distorted as it is squeezed into the sample tube. When the empty sampler begins its downward thrust, the adhesion and friction on the outside of the tube may cause the soil to rise into the tube faster than the tube is descending. On the other hand, after the tube is partly filled, the adhesion and friction between the tube and the sample oppose the rise of the sample. Under extreme conditions, the initial portion of the sample may act as a plug, capable of displacing soft clay seams or layers so that they do not enter the sampler at all. These conditions can be greatly improved by using a piston to close the lower end of the tube until the sampler has been firmly positioned against the undisturbed soils at the bottom of the borehole. The piston is then held at this elevation, in contact with the soil, while the tube is advanced around the piston and into the soil. Initially, the presence of the piston prevents soil from rising into the tube faster than the tube's penetration rate. Later on, downward movement of the soil sample is resisted by a vacuum that develops between the piston and the top of the sample. After the sampling tube has been advanced, the piston is fixed in its new position with respect to the tube. Both elements are rotated to separate the sample from the underlying soil, and the piston and tube are removed from the hole. Piston samplers with small area ratios are capable of furnishing excellent samples of cohesive soils, even if very soft and sensitive. The necessity for a separate piston rod rising through the drill rods to the ground surface can be eliminated by using a hydraulically operated mechanism such as the Osterberg piston sampler. Thin-walled tubes generally cannot be used in very stiff or compact soils without damaging the cutting edge or buckling the tube. Even if a tube could penetrate such soils, the resulting disturbance would be excessive. Under these circumstances, the pitcher sampler, in which rock coring techniques are adapted to tube sampling techniques, may provide better samples. While the pitcher sampler is being lowered into the hole, the thin-walled tube is suspended from the cutter barrel, and drilling fluid circulates downward through the tube and flushes the cuttings from the bottom of the hole. When the tube encounters the bottom of the hole, it is pushed upward into the cutter barrel, while the circulation is diverted outside the tube into the annular space between the tube and the rotating cutter barrel. If the soil is soft, the spring at the head of the tube keeps the cutting edge of the tube below the cutter barrel, and the tube is pushed into the soil just like ordinary tube sampling.